Are we awake? No? The time hasn't even changed yet. 10-year-olds. Why does it feel like 5 a.m. outside? It's only because of the time of day. It's starting to be fall outside. I think I'm probably like one of the only people who actually likes when it gets dark early and it stays dark late. I love that. I like it. Setting myself up for winter hibernation. I wish we could hibernate as humans. Just like go and like curl into a ball for 3 or 4 months and hibernate. That would be wonderful. All right, so let's go ahead and get started before I actually talk myself into going and taking a nap. Let's go ahead and get started on some material. Holy cow, there's like nobody here. Probably less than half the class. Oh my gosh. A third of the class here. That's really not good. All right, well, I guess it is what it is. We'll have to deal with it. All right, so today we want to go ahead and finish up talking about the cardiovascular system. So remember that you do have your test a week from today. It is exam 3. A little bit different. Is that door not open? Is that door locked? The door locked? Cardiovascular system. We've talked about the heart so far. We've talked about blood vessels and the dynamics of blood flow through those blood vessels in terms of Poiseuille's law, resistance to flow, the effects of blood vessel diameter on blood flow and things like that, right? So we've covered a lot of material. The last thing we really need to talk about is blood. Again, your exam is on Wednesday of next week, so we're kind of breaking the pattern just a little bit of having exams on Fridays. It might feel a little bit weird. I think it probably will for me, but it's just the way that the scheduling worked out. There's really not much else there. So the goal for this week is to finish our material and then leave some time for review for the exam on Wednesday of next week. So that's what I want to do. The other thing that I want to do this week is, I'm sure that you guys have looked at your syllabus. You'll notice that on your syllabus is a final project. I wanted to wait to talk about that until we had a little bit of the class behind us before you get some knowledge behind you. So I want to talk a little bit on Friday morning in lecture. I want to talk a little bit about that final project and what that's going to look like. The good news is you've already done part of it, and you just don't realize that you've already done part of it, but I'll explain more about that on Friday. So a little bit of it's done, and then there's a little bit left to do, so it shouldn't be too bad. And hopefully it'll be fun for you, so that's kind of the idea. All right, so with all of that said, are there any questions before we get started? All right, so let's go ahead then and talk about blood. The goal is to kind of lecture about the majority of this stuff this morning in class. And then in lab today, what we'll do is we'll have a chance to get our hands on some materials related to blood and start to learn to identify white blood cells and things like that. So blood is a little bit unique. It is the only fluid tissue in the body. All of our other tissues are either solid or semi-solid, but blood is the only tissue in the body that is fluid. Does anybody remember from 50A what type of tissue blood is classified as? You said it. I just can't hear. Connective. Yeah. Okay, I thought I heard it. Connective. Yeah, blood is a connective tissue. which might seem a little bit strange because, you know, I think bone makes a lot of sense as a connective tissue. You know, obviously our tendons and ligaments are like the epitome of a connective tissue because they're very clearly connecting two things to each other. But blood is also classified as a connective tissue because if you remember from 50A, our definition of a connective tissue is that a connective tissue is a group of cells that are suspended in some sort of a matrix, right? So with bone, we had osteoblasts and osteocytes that were suspended in a hard mineralized matrix. Hyaline cartilage, you had these chondrocytes suspended in a gelatinous matrix, right, that's semi-solid. And then tendons and ligaments, of course, we have fibroblasts that are suspended in a matrix of collagen fibers that are either regularly aligned to make dense, regular connective tissue, or they're irregularly aligned to make irregular, dense connective tissue, or a realer connective tissue, right? So we have all of these cells suspended in different kinds of matrix. We have the same thing with blood, okay? The cells, we're going to spend some time today talking about those cells, but we just kind of generally refer to our blood cells as the formed elements. And then the matrix, of course, is fluid. It's the blood plasma, right? So it fits the definition, even though it might not necessarily seem like a connective tissue at first glance. So let's go ahead and take a little bit of a look at the composition of our blood. We'll come back to those two slides in just a couple of minutes. Let's go ahead and take a look at the composition of our blood. So in addition to having a pretty well-defined composition, one of the really cool things about blood is that its composition is also really easy to visualize, right? Because it is fluid, we can take advantage of tools that we have in the lab to be able to visualize or physically see its composition. We can't really do that with bone or tendons and ligaments and things like that, at least not as easily. But with blood, we can actually do that pretty easily with some really basic lab tools, and it really only takes a couple of minutes. So what we're doing here is we're taking a sample of blood from our arm, a very large needle, and we're putting that sample of blood into this machine that you see right here. This machine is called a centrifuge. So probably some of you guys have used centrifuges, depending on what you've done for work and the lab experience that you've had. But if you haven't, what a centrifuge is it's a machine that will take a liquid sample, a fluid sample, and it will spin it at a really high rate of speed. What it usually will do is it will take that test tube of, well, in this case, blood, and it will hold it either straight to where it's flat out, or it will hold it at an angle like they show kind of in this diagram right here. And when you have a solution that has multiple parts to it, what that centrifuge will do is it will separate the components of that solution based on their weight. Okay? So the heavier things in the solution will get pulled to the bottom of the test tube, and then as we go up, the things that are lighter will be clustered towards the top. So when we pull our blood out of the centrifuge, what we see is something that looks like this, where those formed elements, those blood cells that are the heaviest things in the test tube, are down here at the very bottom, and then the lighter stuff, the blood plasma, is up at the top. Okay? So again, a super easy thing for us to do, a super common thing to do, and one that allows us to visualize the components of our blood very easily. So let's look at the components of our blood then. So if we've got our test tube right here, okay, we've got our test tube right here, and what we've done is we've spun that fluid down to where we've got like this, and then we've got our blood cells like this. those lines. Then we have our, I'm going to go ahead and just do this. I don't really have a good color for this, but I'm just going to go ahead and just kind of do that really quickly just to sort of make this sort of drawing complete. I'll explain it in just a minute. So what we do is when we spin down a sample of blood like this in a centrifuge, we can visualize the components. And we see that our formed elements make up roughly 45% of the total blood volume. Okay? Our formed elements make up about 45% of the total blood volume. And then the other 55 is going to be the blood plasma. Okay.
What was the 45%?
Blood volume. Oh,
Like.
sorry. Thank you. You need to go into hibernation, I'm telling you. 45% formed elements. Try that instead. Okay. 45% formed elements, 55% blood plasma. Okay. All right. So what we want to do today is we want to go ahead and talk a little bit about the different parts of the blood that we see. What are the formed elements? We want to familiarize ourselves with those a little bit. We also want to familiarize ourselves with the types of things that we might find in our blood plasma as well. Okay. So let's go ahead first and take a look at the formed elements. So I'm going to come over here. Let's take a look at the formed elements. So there's multiple cells that we find in our blood. Okay. The first one, the most plentiful, are going to be our red blood cells. Our red blood cells, we sometimes abbreviate them as RBCs. Easier than writing it out all the time. And then, of course, their real name is the erythrocytes. It's erythrocytes, right? So the red blood cells, or the erythrocytes, are one of our formed elements. They're far and away the most common of the formed elements. They outnumber all the rest by a really, really large margin. Okay. We also have our white blood cells. Okay. Our white blood cells, of course, we abbreviate those as WBCs, or we call them leukocytes. That prefix leuko means white. Okay. So white blood cells are leukocytes. And then the very last part of our formed elements, the one that we have to think about, are our platelets or our thrombocytes. Thrombocytes. Okay. I don't really have a good abbreviation for those. So those are our formed elements, three major groups of things that we're going to find that make up that roughly 45% of our blood volume. And again, those are the heavier things, and as a result, when we spin down that sample in the centrifuge, they are pulled to the bottom of the test tube. Okay? So one of the things I want to do today is I want to go through each of these groups of cells and kind of introduce you to them just a little bit. As far as the red blood cells go, we're going to introduce them today, but when we get to the respiratory system in our next unit, we'll talk about them in a lot more detail. White blood cells, we're going to spend some time today learning to identify the different types of white blood cells, but when you take microbiology, you should be talking about the immune system a lot more, and you'll talk a little bit more about the specific roles of those. And then what we're going to do as well today is we're going to really briefly introduce the whole idea of blood clotting and kind of give you guys some information on that as well. So we'll talk about those guys as well. Okay. And then, like I said, of course, we have our blood plasma. We'll talk about that today too. All right. So your red blood cells, let's go ahead and talk about red blood cells really quickly. Your red blood cells are easily the most plentiful cell in your blood. Let me get some pins. I'll go over here and talk for a little bit. So red blood cells are easily the most plentiful cell in your blood. They are one of the smallest cells in our body. Okay. Your red blood cells, or your erythrocytes, are these really small discs that we find in your blood plasma. I'm a little hesitant to even call them cells, even though they technically are. But they're these very small discs, and they're what we call biconcave, meaning that on both sides, the center of the cell sort of caves in a little bit, almost like a donut or a bagel, but the hole just isn't quite complete, right? It caves in at the middle, but the hole doesn't go all the way through the cell, right? We'll get a chance to look at these guys under the microscope today. And what we'll see is that they do look like little tiny donuts. And probably all of you guys would have seen these guys in 50A when we did that lab on blood cells and osmolarity. You guys remember doing that, where you put red blood cells in salt water and hypoosmotic and hyperosmotic solutions, right? So we've seen these guys under the microscope before. But very, very small little cells. They're small biconcave discs, right? So they're small. Small biconcave discs. One of the things that makes erythrocytes probably the most unique among our cells is they are anucleate, meaning that they don't have a nucleus. Okay? We'll talk a little bit about the development of red blood cells, but suffice it to say, fairly late in their development, the nucleus actually gets kicked out of the cell, it gets pushed out of the cell, along with most of the organelles. Okay? So they're anucleate, meaning that there's no nucleus. All right, that prefix A means without, so they're without a nucleus. They also have few organelles as well. They're anucleate, they have very few organelles. So what is in our red blood cells? Well, what we find filling up the majority of our red blood cells then is a protein called hemoglobin. Okay? So they're small biconcave discs, they're anucleate, and they're filled with a protein called hemoglobin. Filled with a protein called hemoglobin. Hemoglobin. We're going to talk about it extensively in the respiratory system in a couple of days. But for now, let's just go ahead and talk a little tiny bit about hemoglobin. Okay? So hemoglobin, as it goes, is actually a fairly large protein. I know it's kind of hard to sort of visualize that, but it actually is fairly large. I know in 50A, and I'm guessing also in Bio 1, you guys learned about different levels of protein structure. You have primary, secondary, tertiary. Well, it turns out that hemoglobin has one of the few proteins in our body that has a quaternary structure, meaning that there's more than one amino acid chain that sort of make it up. So when we take a look at hemoglobin, okay, when you take a look at hemoglobin, you see that there's one, two, three, four amino acid chains that make it up. I just did them in different colors to make sure that you see the different colors. But there's four different amino acid chains that make up this protein hemoglobin. Okay? So it's really large, okay? And its primary job is to bind to oxygen, okay? So this is the primary protein in our body that carries oxygen to our tissues. And again, we'll expand on this idea a lot when we talk about the respiratory system. But hemoglobin does have 4 subunits, 1, 2, 3, 4 subunits. And each one of those can carry 1 oxygen molecule. So what we see is that oxygen can bind to this one, oxygen can bind to this one, and to this one, and to this one, right? So we have 4 oxygen binding sites. Okay. Additionally, the primary component, or a primary component of hemoglobin is that each one of these subunits also has a molecule of iron on it as well. So we're going to see that there's a little iron, Fe, in the middle of each one of these. It's not done. Just made that one up. But anyway, we have a little molecule of iron in each one of those. You may or may not be aware, but when it becomes oxidized, iron takes on a red color, right? So that iron in our hemoglobin is what makes our blood red. Okay, it's the iron in the hemoglobin that makes our blood red. If you've ever been like to Zion or Bryce Canyon or Moab Arches National Park, you've seen all that red rock, Sedona, right? All the red rock in the southwest. That's due to a really high iron content in that rock. When it becomes oxidized, the rock takes on a red coloration. The only real difference is that there's a lot more iron in your blood, and as a result, it has a much more brilliant red color to it. Okay. Because the hemoglobin in your red blood cells is what makes your blood red, your blood is always red. Okay, your blood is always red. But it does vary in color just a little bit in terms of its shade of red. Arterial blood, systemic arterial blood, which is oxygen rich, has a bright scarlet color to it. Okay, whereas deoxygenated venous blood has a much duller color red to it. So it does vary in terms of its shade of red just a little bit, right? So it can vary. Blood varies in its shade of red depending on oxygen. Varies in its shade of red. You guys might have heard as little kids. Little kids like to tell this one. I know I heard it when I was probably in the 2nd or 3rd grade. That your blood is blue until it hits air, right? Have you guys ever heard that one? Right? Your blood is blue until it hits air. I guess I was a skeptic from the beginning because I was like, well, if you cut yourself really fast and take a really close look, can you see it before it turns red? No, it's instantaneous. You can't see it. I'm like, oh, man. I always wanted to believe that that was true, that there was like this magic chemical reaction that happened when your blood hit air and it turned that way. But it turns out that that's just an urban myth, a childhood story. Your blood is always red, and it has to do with, but it does change the shade of blood depending on how much oxygen is in it. The only reason when you look at your arms and you see those bluish colored blood vessels is because you're looking at your blood vessels through your skin, and it does change the color of them just a little bit, but the blood itself never changes color; it's always red. Okay. Yeah.
What was the second blood you named? The first one was systemic arterial, and the second one was
Venus.
venous blood.
All right. So anyway, we have erythrocytes, right? I want to try to get you guys oriented to how many of these red blood cells you have in your blood. Okay. So we see here that we spin them down. We're looking at a whole bunch of red blood cells that have piled up on each other. But I want you to maybe try, just for a second here, try this. I don't know if this is going to work or not. Hey, it does work. I've never used the document camera in this room before, so this is the first for me. Let's go ahead and really quickly, I'm going to pull out a meter stick, okay? Meter, right? Because remember your unit conversions from 50A? I know you do. I know you haven't forgotten them. How many centimeters are there in a meter? Centa is 100, right? Yeah, I know. It's like a bad memory, right? But if we go to the end of our meter stick here, how in the heck? Zoom. See if we can make this work, right? So here I am at 90 centimeters. I get an additional 10 right there, and there's my meter, right, with 100 centimeters. This meter stick has obviously seen some stuff. It's been around for a while, so it's got the edges worn off and things like that, but nevertheless, right? So you'll notice that my centimeters here, okay, I'm going from, oh, I can even go farther. Look at that fine optical quality of this camera. Let's go ahead and make it straight. That's going to bug me if it's not. Okay, so you've got, 90 centimeters here, 91 centimeters, 92, and so forth, all the way up to 99, and then finally 100 centimeters and your full meter, right? But you'll notice that each of those centimeters is broken down further into tens, right? So what's a tenth of a centimeter? A what? A millimeter, right? Yeah. So, if I hold my finger up here really quickly, you'll see compared to that width of my fingernail just how big a millimeter is, right? We know that they're very, very, very small, okay? So if you guys would do me a favor, imagine that on your desk, in front of you right now, you've got a box. And that box is a perfect square, and it happens to be 1 millimeter on each side. So it's a really, really small box, okay? You guys with me? You got your 1 millimeter cube on your bench in front of you. Okay. Now imagine that you put blood. You fill up that box with your blood. Okay. Now here's the thing, right? That box is so small that not even a full drop of blood is going to fit in it. Okay. You would need 20 of those boxes roughly to fit an entire drop of your blood in it. Okay. So we're talking a really small box here. Okay, you guys all with me so far? Okay, so you're getting about 1/20th of a drop of your blood into your box, but it's filled. Okay, cubic millimeter of blood. Inside of that box, you're going to find roughly 5 million red blood cells. 5 million red blood cells. These erythrocytes. We're going to find roughly 5 million in that cubic millimeter of blood that you now have sitting on your desk. I want that to sink in for a minute. 5 million. I don't think sometimes that we really appreciate how big of a number a million is. But it's a big number, right? We talk about millionaires all the time, and we talk about wanting to earn $1 million a year and things like that. But do you know how big of a number a million is? You know how long a million seconds is? It's 11 days. So if you were able to count once per second, right? 1, 2, 3. It would take you 11 full days with no breaks to get to 1 million. You have 5 million red blood cells in that cubic millimeter box that you have on your desk in front of you. So that means if you were to take them all out one at a time, 1 per second, and count them to prove me right? It would take you 55 days to count all of them. Does that blow anybody else's mind? Just a little tiny bit? Thank you. I appreciate you saying that. If I haven't blown your mind yet, let me try to go a step farther, okay? Inside of those red blood cells, you have hemoglobin, okay? Inside of those red blood cells, you have hemoglobin. Now, do me a favor, and take out of that box in front of you, take out one red blood cell, okay? So you still effectively have 5 million in your box, right? Because you just took out one. Inside of that one red blood cell, you're going to find about 250 million hemoglobin molecules. About 250 million hemoglobin molecules per red blood cell. Okay, let's do a little bit of math, okay? If each one of them combined 4 oxygen, how many total oxygen can you fit in a red blood cell? What's 250 million times 4? A billion. A billion. That means in one red blood cell, remember on your box in front of you, you've got 5 million of them in 1 cubic millimeter of blood. In one red blood cell, you can fit a billion oxygen molecules. A billion. You know how long a billion seconds is? Do we understand the difference between a million and a billion? Many of you, most of you, haven't even seen a billion seconds in your lifetime yet. It's about 34 years. That's one red blood cell. You take out one red blood cell from your box, and it's going to take you 34 years just to count the oxygen molecule bound to that hemoglobin. That's crazy. That's how small the stuff that we're talking about in this class is. Right? It's real easy to visualize it like, oh, it's just an oxygen. No, we're talking about something that's really, really small here. Okay? Like really small. So that means in that box, if you can fit 5 billion red blood cells in there, and you've got a billion oxygen molecules on one red blood cell, and you've got 5 million red blood cells in your box, how many oxygen can you fit inside of that entire box? What's a billion times 5 million? I'm not even going to try to do that. Is it 5 million billion? Can we say that? I think we can say that, right? 5 million billion oxygen molecules in 1 cubic millimeter of your blood. You have about, what, 5 liters of blood in your body? That's a lot of cubic millimeters of blood, okay? That's crazy, right? That's crazy. We're talking about numbers now that we can't even really understand, right? We're talking about huge numbers. Want another big number that's only sort of related to this? Okay, so salt, right? Table salt, okay? Imagine in your hand you've got 1 grain of table salt, okay? So what is table salt, right? It's sodium and chloride, okay? There are more sodium and chloride atoms in that single grain of table salt than there are grains of sand in every beach on Earth. Than every beach on Earth. So, I don't know. That one, yeah. Big numbers, fun numbers, right? It's fun to think about things that are that small and numbers that are that big inside of our body, right? So when I said at the very beginning of the semester that we literally have trillions of chemical reactions happening in our body every single second, we really do, right? I'm not even going to go down the road of how big a trillion is, right? I'll let you guys do that in your own time. But the number of chemical reactions happening in your body at this second, as you're sitting right here, that number is so big that like, and this isn't an insult to you, but you can't even comprehend that number. It's so big, right? So it's just insanity to me. And I think that's one of the really cool things about this class is we start to think about the scale of things that are happening inside of us. And I don't think it really matters what your personal beliefs are. I mean, that's nothing short of miraculous, right? The scale of things that's happening inside of you and the number of things that need to be happening at once just to keep you alive in this moment is really remarkable. Okay. So anyway, it's pretty crazy stuff. At any rate, let's go ahead and come back to reality for a minute. Let's ground ourselves in some numbers that we can actually measure and understand. That's really impressive, but it's not a practical measure, right? One of the things that we do care about, though, is we do care how much hemoglobin is in your blood, okay? In fact, part of a normal blood panel is going to be measuring that. So what we usually do is we usually measure the hemoglobin concentration in grams of hemoglobin per 100 milliliters of blood, or per deciliter of blood, okay? So normal levels of hemoglobin should be somewhere between 12 and 18 grams per 100 milliliters of blood. Okay? That's kind of what we're normally looking at for that, right? It turns out that because iron is an important component of hemoglobin, it tends to be a fairly heavy molecule, and so that's why that number is as big as it is, right? 18 grams is actually fairly large. So your blood is fairly dense, as it turns out. Low hemoglobin concentration, right? If this number were too low, it could be indicative of a shortage of iron. What do we call it when we have a shortage of iron? Anemia, right? We call it anemia. So if this number, your hemoglobin concentration is too low, it could be indicative of anemia. There are lots of different types of anemia, lots of different ways that they can come about. But it's a good umbrella term for a shortage of iron. Okay? When we don't have enough iron, our oxygen carrying capacity of our blood is inhibited, and that causes all sorts of problems with oxygen delivery to our cells. But if this number is low, it could be indicative of some form of anemia. Okay. The other thing that we can do very easily is we can also measure our, we can also just simply take this measurement right here, okay? The majority of what we're looking at right here is red blood cells. Your red blood cells outnumber your white blood cells by a huge margin, okay? And so when we spin down our blood, we do see a very thin layer of white blood cells that forms right here. This is called the buffy coat. Called the buffy coat, and those are your white blood cells. But it's really thin, and the majority of the rest of this is red blood cells. So we can also just simply put a sample of blood in a centrifuge. We can spin it down at 50,000 RPM for 2 or 3 minutes. We can measure the percentage of blood volume occupied by our red blood cells. This measurement is called our hematocrit, okay? So this measurement is called our hematocrit. One thing I don't think about this very much space to write. Hematocrit, okay? Hematocrit is the percentage of blood volume occupied by erythrocytes. And it should be somewhere around 45 to maybe 50%. Okay? It should be somewhere around 45 to 50%. Obviously, a little bit lower than that or a little bit higher than that is something that we are just fine with. But it should be So in this particular sample, we're looking at a hematocrit of about 45%. Again, if this number is too low, okay, that would be indicative of an anemic state. You don't have enough iron to make enough red blood cells, and the oxygen carrying capacity of your blood is impaired, right? So a lot of times when we see a low hematocrit, we also see a low hemoglobin concentration. Those two things usually go hand in hand with each other, right? And again, both of them low would both mean, anemia. So we'll put here if this is low, it could be anemia. If it's high, a hemoglobin or a hematocrit that's too high results in a condition called polycythemia. We'll talk more about that a little bit more when we talk about the respiratory system, actually. But it's polycythemia is the condition there. And that can actually put a lot of stress on our heart and things like that. Okay. So, red blood cells, number 4 to 6 million per cubic millimeter. I gave you the number of 5 million that you have in the box on your desk in front of you. But of course that can vary just a little bit, right? And then again, their primary job is to transport oxygen. To a lesser degree, our red blood cells do help to carry carbon dioxide, and we'll expand on that when we talk about the respiratory system. Your white blood cells, your leukocytes, there are many types of them. We'll talk about those types today in lab. But suffice it for right now to say, on that box that you have in front of you on your desk that's filled with a cubic millimeter of blood, you have somewhere between 4 and 11,000 white blood cells. Okay. It's a big difference, right? 5 million red blood cells, somewhere between 4 and 11,000 white blood cells, right? So paltry numbers, right? Still impressive, but way fewer. And then of course we have those platelets, those thrombocytes that are involved in blood clotting, somewhere between 250,000 and 500,000 of those. Okay. So those are our formed elements. Let me actually put platelets into this as well. This is white blood cells plus platelets. Sorry about that. I don't want to forget platelets. Okay. And then, of course, we have your blood plasma, which has a fairly unique composition. We'll talk about that here right now. So let's look at blood just a little bit more, and then I've gotten out of order. I got excited about red blood cells. So blood, in general, has a characteristic metallic taste to it. I'm sure that you guys have probably all, licked a scratch or something like that to get it to stop bleeding or something like that at some point in your lives or something like that. I have a 10-year-old right now who I think legitimately thinks he's a vampire. And anytime he cuts himself, he's like, or if I cut myself, he's like, can I lick it? No, don't be weird. You're not allowed to do that. And then he talks about doing it on the playground. He's like, so-and-so cut his knee today, and I asked if I could lick it. And I'm like, you're not allowed to lick your friend's wounds. Don't even go down that road. But I think he legitimately thinks he's a vampire. He said he admitted to one of his friends his secret. And I said, what? And he said, I told Franz my secret the other day. I said, what's your secret? He says, and I'm like, oh my gosh. Anyway, it does have a characteristic metallic taste. Not accusing anybody of being a vampire, but it does have a characteristic metallic taste. I'm sure you know that. There's a lot of metallic ions in our blood, like sodium and chloride, that do give it its metallic taste. Almost salty in a way. I've mentioned that it varies in color. It also is slightly basic. It runs from a pH of 7.35 to 7.45. And also, probably because of its density with all of the iron in it, your blood also runs a little bit warmer than body temperature. Our body temperature is about 98.6 degrees Fahrenheit, whereas our blood runs about 100.4 degrees. So we're looking at a little bit more than 2 degrees above our body temperature. And again, that probably has to do with its density compared to other tissues in the body. And then again, our average blood volume is somewhere between 5 and 6 liters of blood. Obviously, that one varies quite a bit based on body size, right? Where larger people are going to have more blood, smaller people are just naturally going to have less blood. But generally speaking, you're looking at somewhere between 5 to 6 liters of blood. Okay. Let's take a look at blood plasma really quickly. Get through some of this. Blood plasma. Our blood plasma contains a lot of different things that are dissolved in it. So, nutrients are one thing that's dissolved in our blood plasma. So in this region up here, we're going to find nutrients dissolved in it. I mean, all semester long, we've been talking about things like blood glucose levels, right? That's a nutrient that we would find dissolved in our blood plasma. Glucose is a great example. Salts, ions, right? Sodium, chloride. We've been talking about blood calcium regulation. What else? I'm trying to think. Magnesium, right? All of these things that we find in our blood. We do find a little bit of oxygen and carbon dioxide dissolved in our blood. Those are respiratory gases. Hormones, right? We just spent the end of our last unit talking about the fact that hormones are these chemicals that are carried around in our bloodstream, right? So at any given moment, if we were to take a look at your own blood, we'd find that there are certain hormones that are dissolved in it. Okay. We also have plasma proteins, okay? There are a number of different plasma proteins. I'll back up to a slide here in just a minute that sort of outlines those. But suffice it to say, the proteins in your plasma are the most plentiful, the most prevalent solute in your blood. Okay? I think we mentioned this the other day, right? But let's make sure that it's underlined in our notes that your plasma proteins are the most plentiful substance in your blood plasma by a long shot. Plasma proteins are the most prevalent solute in your blood plasma, right? The most prevalent solute in your blood plasma. They're the contributor to that colloid osmotic pressure that we saw last week that pulls fluid into our capillaries, right? So we saw at the very end of our unit on blood vessels, or our lecture on blood vessels, that colloid osmotic pressure pulling fluid into our capillaries. And then of course you have waste products in your blood, right? After exercise, for instance, you're going to find lactic acid in your blood. Great example of a waste product that you might find in your blood, or other things as well, right? So a number of things that we find in our blood plasma.
Did you say O2 and CO2 are the respiratory gases?
They are. So plasma proteins are the most abundant, and the composition of our blood plasma changes on an almost continual basis, right? If I were to take a sample of your blood plasma when you wake up in the morning, it probably would be very different than what you have right now. And it would probably be different than what you would have before you go to bed tonight, right? If we look at hormone levels after lunch today, right? You're going to have a spike in blood glucose levels. So we're going to see glucose levels in the blood rising after a meal, right? So the composition of our blood plasma is not static. It's changing all the time depending on what we're doing and things like that. Just real quick, I'm not going to spend a ton of time on this slide, but I did include a slide here where I actually talk about your different plasma proteins. So there's a number of them here, like the albumin. Albumin is probably the most important of all of them, but there's a few others as well. I'll kind of refer back to this a little bit later on, but I'm not going to spend a ton of time on it right now. But I tried to kind of summarize some important things here for us so that we have a little bit of a reference chart here. So it's kind of like the map in the front of the book that you need to be able to follow along, right? So erythrocytes, I've already talked about those. I've already tried to wow you as much as I possibly can. And then white blood cells. Okay, so let's talk for a minute about our white blood cells. This will kind of lead us into lab this morning. Our leukocytes, their primary job is in the immune system, okay? They can consist of maybe 1% of our total blood volume. Like I said, the numbers of them are way, way less than what we see for red blood cells. Again, in that box that you have on your desk, you're only looking at maybe 4 to 11,000 of these guys, as opposed to 5 million red blood cells. That number is also fairly is a fairly wide range, right? 4 to 11,000 is a fairly big range. Just like your blood plasma, the numbers of your white blood cells can change considerably depending on what might be going on, right? They all have very specific jobs. So if you're fighting the flu, for instance, you're going to see a peak in certain types of white blood cells. Whereas if you've got malaria, which is a blood parasite, you're going to see a peak in different types of white blood cells, right? So the numbers of them can vary, and they are produced kind of based on the specific demands of your body at any given period of time. And today in lab we'll elaborate on that just a little bit. Our white blood cells are normal cells, at least anatomically, right? They've all got a nucleus, as opposed to our red blood cells, which don't. But they've all got a nucleus. They've all got kind of all of the organelles that you would expect to find in any given cell. You've got your mitochondria, and your endoplasmic reticula, and your Golgi apparatus, and things like that. One thing that is really unique, though, about white blood cells is that they have the ability to travel in tissues that aren't our blood. So I guess every blood cell needs a special. It's like Marvel, right? We all need a special power. The special power of white blood cells is the ability to travel out of our blood vessels, right? Obviously, if I were to take a sample of blood from you right now, I would find many, many white blood cells. But if I were to take a sample of your extracellular fluid, the fluid around your cells, I'd find white blood cells. If I were to take a sample of your cerebrospinal fluid, I'd find white blood cells. If I were to look in your lymph, which is that fluid that accumulates, that leaks out of our capillaries and is returned to our circulatory system, I'd find white blood cells, right? So even in our non-blood tissues, we're going to find white blood cells. So they're kind of everywhere in our body, not just our blood. And the ability to move in and out of our blood vessels is called diapedesis. Right? So what they do is they just kind of squeeze between those endothelial cells of our blood vessels, and then they're able to move out into non-blood tissues. They have the ability, when they're moving around inside of our body, they actually have the ability to move towards areas of damage, okay? So I use that term damage kind of loosely here. It could mean that we have a cell that's been infected with a virus and that virus is replicating inside of it. It could mean physical damage, like the cell has been broken, like you've cut yourself or something like that. It could mean a number of things. But regardless, when a cell has been damaged, right, it's going to release chemicals that essentially are going to ask for help. Okay, our white blood cells, certain types of our white blood cells are exceptionally good at detecting these signals and then congregating in that space so that they can help to heal the cell or fight the infection or whatever. Okay, so what we have then is we have, in areas that are damaged, we'll have kind of a large number of white blood cells that start to gather. This is actually one of the big things that happens, or that accounts for inflammation, right? Swelling, a lot of times is just due to the fact that a lot of white blood cells are coming into a particular area. When you get sick, your lymph nodes become inflamed as well, right? Now, inflammation in your lymph nodes is due to the fact that white blood cells are congregating in that area, okay? So kind of an interesting thing. The ability to do that is called positive chemotaxis, okay? So that word chemotaxis, the suffix taxis means to orient yourself to something. And chemo is referring to a chemical signal. So you're orienting yourself to a chemical signal. And positive chemotaxis means that you're going towards the source of the signal, right? So, like you might do in the morning when you wake up and you smell the coffee on in the other room, you go to find who has the coffee, right? Or the bacon or whatever. Something like that. You know, that would be positive chemotaxis as well. You're moving towards the source of that chemical signal, right? Whereas if the person next to you toots and it's kind of stinky and you have to like scoot away from them a little bit, that would be negative chemotaxis, right? Because you're moving away from the source of the chemical signal, right? I'm not suggesting any of you have tooted. I haven't smelled anything this morning that would give me evidence to suggest that. When your white blood cells are in your blood, they're just carried along in your blood. But when they're not in our blood, when they're in non-blood tissue, they also can move around. Excuse me. I told a bad joke and made myself laugh, and now I'm coughing. So when they're in your non-blood tissues, they have to move around somehow. And they do that via amoeboid motion, right? So the easiest way to envision amoeboid motion is to think about the blob. Have anybody ever seen the movie The Blob? It's a good one, right? I think that should be your homework, is to go watch The Blob this weekend. It's the season for it, and it's a good, like, campy old horror movie. It's a good one. But the blob moves by amoeboid motion. It just kind of creeps along like a gelatinous mass, and that's how your white blood cells move around when they're not in your blood. Okay. So a couple of different classifications of white blood cells. What I'm going to do is I'm actually going to, I think it's 9 o'clock right now, I'm going to talk about this in lab, and then what we'll do is we'll get some practice today under the microscope identifying these white blood